So in section 4, we're going to start talking about sampling distributions for sample means, just like we did with proportions. So a couple things to just keep in mind when we talk about means. Averages are less variable than individual observations, and they are more normal than individual observations. So there are a couple upsides to means than proportions. So a couple of things as to why that's important is because if we were to look at a histogram of averages, we'll get a histogram that is more normal and less spread out than a histogram of individual observations. So data is much easier to work with if it's normal and has a small spread. So it's to our advantage to look at a distribution of averages. So when we're deciding between means and proportions are typically used for categorical data. Proportions are very good when it comes to categorical data. Means are what we're going to use to compute quantitative data. So that means data that is numerical in design. So let's go over a couple of the terms. So we're going to use mu to represent our population mean. Sometimes we'll know it, but most of the time it's unknown, very similar to our proportion parameter. We'll use sigma to represent our population standard deviation. We use x bar to represent our sample mean, which is our most common statistical measure, and then s sub x bar to represent our sample standard deviation. So we have used all four of these before in previous chapters, so we're just reviewing them now. So let's talk about mean and standard deviation for a sampling distribution for sample means. So if x bar is the mean of an SRS with size n drawn from a large population that has mean mu and standard deviation sigma, then we know from a proportion that the mean of our sample proportion p hat is equal to our population proportion p. So it's very, very similar to for the mean of a sampling distribution. So mu sub x bar equals our population mean mu. Again, this is true as long as it's taken randomly. And then we can say that it's unbiased. When it comes to standard deviation, we know the standard deviation for a sample proportion is the square root of p times 1 minus p all over n. For a sampling distribution for x bar, it's a much easier formula. S sub x bar is equal to the population standard deviation over the square root of n. Much nicer formula than for proportions. So the sampling distribution is going to have a smaller spread than the population, and it gets smaller as your sample size increases. So if you draw an SRS of size n from a population that has a normal distribution with your population mean mu and your standard deviation sigma, then the sample mean follows a normal distribution with a mean of mu and our standard deviation is this population standard deviation over the square root of n. Next, we're going to talk about our conditions. So we still have the same three conditions that we had for a proportion. It has to be random, independent, and normal. However, one of these conditions is checked differently than it was for proportions. So for random, as long as the sampling method is random, our mean is an unbiased estimator. For independent, we still have to make sure our 10% condition is satisfied. If we're not sampling, the problem has to state that our trials are independent. So our 10% condition is n is less than or equal to 0.1 of our population n. For normal, we don't actually use the large counts condition anymore. For means, they have a different one. So for proportions, we could use a normal approximation as long as the sample satisfied our large counts condition, which meant we had a large enough sample size. For means, we still have to have a large enough sample size, but the condition is different because the shape of the sampling distribution depends on the shape of the population distribution. And this is only true for means. It is not true for proportions. So most population distributions are not normal. So we want to know what's the shape of the sampling distribution for your sample mean when the population distribution isn't normal. It can be proven, but we're not going to do it now, that as the sample size increases, it will look less like that of the population and more like a normal distribution. So when the sample size is large enough, the sampling distribution is very close to normal, and it's called the central limit theorem, which says that when n is large, the sampling distribution of the sample mean is approximately normal, no matter what shape your population is. So when it came to how big is large enough, it does depend on the population shape, but as a rule of thumb, we use at least 30. So as long as your sample size is at least 30, we can assume that it is a normal distribution. Couple things. If the population distribution is normal, then so is the sampling distribution, no matter what sample size you have. So you only have to check that n is greater than or equal to 30 if you don't already know the population distribution is normal. This should not say x bar greater than or equal to 30. That should say n greater than or equal to 30. That's a typo. So if it's not normal or has an unknown shape, then the sampling distribution is normal if n is greater than or equal to 30, not x bar. So when it comes to doing a problem, it's the same 4 steps that we did for proportions. You have to identify your population parameter. You have to write your probability statement. You have to check your 3 conditions, random, independent, and normal. Then you'll calculate your probability, and then lastly, write your sentence. So let's go ahead and look at an example. Suppose the heights of young women are normally distributed with a mean of 64.5 inches and a standard deviation of 2.5 inches. What is the probability that the mean height of an SRS of 10 young women is greater than 66.5 inches? So we're trying to find the probability that x bar is greater than 66.5. So first we're going to start by checking our conditions. So we are taking an SRS, so we are random. For independent, 10 has to be less than or equal to 10% of all young women, which there's at least 100 of those, so we're good there. And then for normal, it does stated that it is normally distributed. So I don't actually have to check that n is greater than or equal to 30 here, because it is stated in the problem that the population is normally distributed. So that tells me that the mean of my sampling distribution is going to be 64.5. And when I calculate my standard deviation, I'm going to do 2.5 over the square root of 10. Which is 0.7906. Very similar to proportions here. If my standard deviation is not exact, I really don't want to compound that rounding by calculating a z-score. So I'm going to go ahead and go straight to normal CDF to calculate my probability. So my lower bound is going to be negative 1e99. Sorry, nope. I'm doing greater than. My lower bound is 66.5. My upper bound is positive 1e99. Mean is 64.5. Standard deviation is 0.7906, not 4. So you get a second bars You plug in the information, and we are going to get a probability of 0.0057. It's very, very low. So that tells me the probability that an SRS of 10 young women is greater than 66.5 inches tall is 0.0057, which is less than 1%. So it's not very likely, not a very large probability. For our next example, we have that the number of flaws per square yard in a type of carpet material varies with a mean of 1.6 flaws per square yard and a standard deviation of 1.2 flaws per square yard. The population distribution cannot be normal because a count takes only whole number values. An inspector studies 200 square yards of material, records the number of flaws found in each square yard, and calculates X bar, the mean number of flaws per square yard inspected. What is the probability that the mean number of flaws exceeds 2 per square yard? So we're trying to find the probability that X bar is greater than 2. So for random, we are just going to go ahead and assume here, because we're going to assume that because he's studying 200 square yards, we'll just assume that the 200 square yards he chose were random in choice. For independent, our sample size is 200 because that's how many square yards he inspected. Has to be less than or equal to 10% of however many yards of carpet material they have. And we'll go ahead and assume there's more than 2,000 yards of that, because they should be producing a lot of carpet. And then for normal, it does specifically state in the problem that the population is not normal. So we have to check that our sample size 200 is greater than or equal to 30, which it is. So even though we know that our population isn't normal, our sample is. So the mean of our sampling distribution is going to equal to our population, 1.6. And then our standard deviation, we're going to do 1.6 over the square root of 200. And we're going to get 0.1131. And again, not an exact standard deviation. So, sorry, not 1.6. The standard deviation is 1.2. So 1.2 divided by the square root of 200 is going to be 0.0849. So again, not an exact standard deviation, so we're going to go straight to normal CDF. My lower bound will be 2. Upper bound will be 1E99. Mean of 1.6. Standard deviation of 0.0849. Which is going to give us a very, very, very small decimal. It's 1.23, and then it's going to be E negative 6. So that's going to tell me 0.00000, so 5 zeros, 1, 2, 3. So very, very, very small probability here. So for our sentence, the probability, the mean number of flaws exceeds 2 per square yard is 0.0000123. Very, very, very unlikely that it exceeds 2, which I guess is a good thing for quality control purposes, is that it's not a lot of flaws per square yard. All right, so we're going to do one last example. So we have that a certain beverage company is suspected of underfilling its cans of soft drink. The company advertises that its cans contain, on average, 12 ounces of soda with a standard deviation of 0.4 ounces. For the questions that follow, suppose that the company is telling the truth and assume this data follows a normal distribution. So we want to find the probability that a single randomly selected can contains 11.9 ounces or less. So because we're looking at a single can, I don't have to check my conditions. I only have to check my conditions if I'm taking an SRS. But because it's one single can, I don't need to do that. So we're trying to find the probability that X bar is less than or equal to 11.9. So if we go to normal CDF, our lower bound is negative 1E99. Our upper bound is the 11.9. Our mean is 12, and our standard deviation is 0.4. And we get a probability of 0.4013. So that's a pretty large probability that a single randomly selected can contains 11.9 ounces or less. It's pretty high, almost 50%. Now let's suppose that a quality control inspector measures the contents of an SRS of 50 cans of the company's soda and calculates the sample mean. We want to now calculate the mean and standard deviation of a sampling distribution for a sample of size n equals 50. So in order to calculate my mean and standard deviation, I now have to check that all of my conditions are met. So first I have to check random, which it is an SRS, so you are random. For independent, my sample size 50 has to be less than or equal to 10% of all soda cans, and there's going to be at least 500 of those. And then for normal, it does state that it is a normal distribution. So I don't have to check that my sample size is greater than or equal to 30, but it is. So even if I didn't know that the distribution was normal, I still have a large enough sample size. So that tells me that the mean of my sampling distribution is going to be 12, and the standard deviation is going to be 0.4 divided by the square root of 50, which gives us 0.0566. So the inspector that we just talked about in Part B, he obtains a sample mean of 11.9 ounces. So now we want to recalculate the probability that a random sample of 50 cans produces a sample mean of 11.9 ounces or less. So it's still the probability that X bar is less than or equal to 11.9. But when I go to normal CDF, I no longer have the same standard deviation. So my lower bound is still negative 1E99. My upper bound is still 11.9. My mean is still 12. But now my standard deviation is 0.0566. Which is going to give us a probability of 0.0386. which is a lot smaller of a probability than when we looked at a single can. So what would you conclude about whether the company is underfilling its cans of soda? Justify your answer. So since the probability in an SRS of 50 cans contains 11.9 ounces or less is so small, we can conclude the company is not underfilling cans. If I had gotten something similar to when I sampled just one can or something higher, then we can say that the company is underfilling their cans. But since it's only about a 4% chance in that SRS, it's very unlikely. And if I took an SRS of even more cans, that probability would continue to decrease. If I took an SRS of less cans, then it would increase, but it depends on what the SRS is. So let me know if you have any questions about calculating probabilities associated with sampling distributions for meats.